Here we have a vector field and a line segment oriented from P to Q. And the question is about being able to parametrize the line segment and compute the line integral. And then you have this part C, which we will figure out later. So the first task is to orient this line segment. Let's put that on the plane. Let's see what we get. This is 3, 0, so that will be our P. Then 1, 2, 3, 4, 5. This will be our Q, 0, 5. And the path C is this. Okay. So there are two ways to go about parametrizing this. One will be to find the line equation, and then once you have the line equation, you can parametrize it. Let me quickly show you how that's done. You can say the slope is rise over 1, you go down 5, so negative 5, and run is 3, so that's the slope. And because the y-intercept is 5, we know that y equals to negative 5 over 3x plus 5. And once you have this, then you can parametrize this by saying x equals to t, and then y equals to negative 5 over 3t plus 5. So that's one way to do it. The problem with this is they want a parametrization that gives you p when t is 0 and q when t is 1. If you plug in 0, you do get you don't get that. You get 0, 5. So this actually is oriented in the opposite direction. So yeah, and you start at 0, 5, and only when t is 3 you reach 3, 0. So although this is a possible way to parametrize, but then you have to reparametrize this, and that's more confusing. Okay. So let me show you a better method. The better method is to use the line equation in the parametrized form, which is RT is x0, y0, which is the initial point, plus the vector a comma b, which is a direction vector times t. And this line equation, well, I guess I still need to write this as a vector, but this is the initial point, and this is the direction vector. Okay, so let me show you how this thing works. Because we want to start from P and then go to Q, this is our initial. So 3, 0 is what we have. And then to get a comma b, you have to say a comma b vector is it's the vector P to Q, right? Because the line is from P to Q, the direction of the line will be the vector PQ. And whenever you want a vector connecting 2 points, it's always terminal minus initial, so that the terminal is 0, 5, whereas the initial is 3, 0, which is negative 3, 5. Okay, so that's our direction vector. So that gives us let me change the color. Plus negative 3, 5 times t, which is 3, 0 plus negative 3t, 5t, and then you add, that's 3 minus 3t, plus 5t. Okay. Now we still need to check if indeed it's going to be at p and q at time t equal to 0 and t equals to 1. So let's check that. R of 0 would be 3 minus 0 comma 0, right? So indeed it gives you 3 comma 0. And R of 1 would be 3 minus 3 times 1 comma 5 times 1. And 3 minus 3 is 0, and you get 5, so indeed you get 0 comma 5. So we did figure out the path, which is 3 minus 3t comma 5t. Okay, so that's the answer. Now once you have this answer, then now you're ready to compute the line integral. Let's try that. So 3 minus 3t comma 5t is our RT. Let's remember that. And in any integral, in any line integral, the first step is to divide by dt and multiply by dt. That's the first step. Step 1, divide by dt, multiply by dt. And then because now you're integrating by t, the bounds should be from 0 to 1. Oh, I forgot to say, we know that the curve C is from 0 to 1, right? For any line segment or curve, not only you need to provide the function, the parametrized function, but also the bounds for t. Because if you don't have that, then you end up with an infinite line. And most likely, if you integrate some vector field over in infinite line, then you're going to get infinity or negative infinity. So it's not, I mean, sometimes you might get finite, but usually you don't. So it's not something that you would want to do. Okay, so coming back, what is this? Well, you're really evaluating f at here. You're evaluating f at x comma y, but this will be your x and that's your y, right? You're evaluating the vector field at RT. That's how you should think of this. And then dr dt means you're differentiating this. So what do you get if you differentiate this? You get negative 3 comma 5. And then dt. And because RT is 3 minus 3t comma 5t, and 3 minus 3t is x, and y is 5t, x and y are replaced by 5t and 3 minus 3t respectively. So you have the vector field would be negative 5t I plus 3 minus 3t j dotted with negative 3 comma 5. And then furthermore, see, this is really negative 5t comma 3 minus 3t, right? So you're doing the dot product with this and that, which means you multiply component-wise. Negative 5 times negative 3 is 15. So positive 15t plus 15 minus 15, and you're integrating from 0 to 1. And they cancel, and you're just integrating 15 dt, so you get 15t, and you're plugging in 1 and 0, so you get 15 as the answer. Okay, now let's think about what this part C is saying. Part C is saying, now we still have Q and P as before, but we think of the path, which is this triangular path. So it's really, this new triangle is really a sum of 3 paths, so we can call this as C1. C1 is what we had before. This is really like C1. And then we have C2 and C3. So part C is asking you to calculate C1 plus C2 plus C3 of f dot dr, and one of which we do know. It's this, right? So at this time you might think, okay, so in order to figure out C2 and C3, you could use the same strategy to parameterize this line and also that line, which is perfectly fine. You could do it that way. But the hint says, sketch the vector field and the triangle. Well, what is this vector field? See, for example, we have 1 and 2 and 3. So if you had 1, 0, over here 1, 0, that means x is 1 and y is 0, right? And if you evaluate f at 1, 0, you end up with this. This says y is 0, so you get negative 0i, and then plus x is 1, so you get 1j, which is 0, 1, which is a vector pointing upwards, right? And then likewise, if we plug in 2, 0, it will still be a vector field that's going upwards. And after some inspection, you'll see that all the vector fields over this line is always going up, whereas C3 dr is going right. So these the vector field and dr are perpendicular, and therefore the dot product, so you're going to get that integration of C2 of f dot dr, the dot product will be 0 because 90 degrees. Okay, the angle between the two vectors is 90 degrees. And also, if you try drawing it at, say, 0, 1, 0, 2, 0, 3, for example, if you plug in 0, 1, you'll see that the vectors are pointed this way. So again, here the direction which is going down and the vector which is going left, they're perpendicular. So that's also true for C3 f dot dr. Again, it's 90 degrees. So the answer to C would still be 15. It wouldn't change because the integration over C1, C2, C3 is just same as integration over C1, integration over C2, plus integration over C3. But C2 and C3 integrals, they are 0 because the path is perpendicular to the vector field. And that's why the answer to part C will be same as part B.